Hello, I am Dr. Sudha, Associate Professor, Department of Mathematics, Government Science College, Autonomous, Bengaluru. In this session of Algebra 1, Unit 1, Session 2, let us discuss or recapitulate normal subgroups, simple group, center of a group, normalizer of an element of a group, important results on normal subgroups, quotient groups, homomorphism, types of homomorphism, kernel of homomorphism, fundamental theorem of homomorphism. Let us begin with the definition of normal subgroups. A subgroup H of a group G is said to be normal subgroup of G if G inverse belongs to H for every G belongs to G and H belongs to H. Example, the fourth roots of unity 1 minus 1 I minus I and H equal to the square roots of unity 1 and minus 1 is a normal subgroup of G. If G is Z comma plus, that is set of all integers with respect to addition is a group, and H is equal to 2Z, the set of all even integers is a normal subgroup of G. Next, let us move on to the simple group. A group which do not have proper normal subgroups is called simple. So in the previous session, we had seen that a group of prime order do not have proper subgroups. Therefore, a group of prime order is always simple. Important results. A subgroup H of a group G is normal if and only if G inverse is equal to H for every G belongs to G. A subgroup H of a group G is normal if and only if every right coset of H in G is a left coset of H in G. Every subgroup of an abelian group is a normal subgroup. So if you consider a group which is a commutative group, then every subgroup of it will be normal. A subgroup H of a group G is normal in G if and only if product of any two right cosets or any two left cosets of H in G is again a right coset or a left coset of H in G. The centered set of a group G is a normal subgroup of G. And the center Z is given by set of all elements Z belong to G such that Zx is equal to Xz for all X belongs to G. That means this Z contains all those elements which commute with every element of G. Normalizer of any element of a group is a subgroup of the group. And the normalizer of an element A is denoted by NA and it is equal to the set of all elements which belongs to G such that they all commute with the element A. So if every element of NA will be satisfying the commutative law with the element A. The center Z of a group is a normal subgroup of a normalizer of an element. That is, Z is normal in NA. Next, let us move on to the factor group, which is also known as quotient group. Let G be a group and H be a normal subgroup of G. Since H is normal in G, there is no distinction between a right and a left coset. The set of all cosets of H in G is denoted by G by H, and the set G by H will contain all cosets of the form HA, where A belongs to G. G by H is a group under the binary operation defined by HA into HB is equal to HAB for all AB belongs to G. G by H is known as a factor group of G with respect to H, or it is also known as the quotient group of G with respect to H. Let us note down these points here. If H is normal in G and H is of finite order, that means this subgroup H is of finite order, then order of G by H will be equal to order of G divided by order of H. But in Lagrange's theorem, we had seen that order of G divided by order of H is nothing but the index of H in G. So therefore, order of G by H will give us the number of distinct cosets of H in G, or rather it is also known as index of H in G, and that is equal to order of G divided by order of H, and that is the result of Lagrange's theorem for finite groups. Every quotient group of an abelian group is also abelian. Every factor group of a cyclic group is cyclic. Let us move on to the homomorphism of groups. Let G comma dot and G dash comma star be two groups. A mapping F from G to G dash is said to be a homomorphism if F of G1 dot G2 is equal to F of G1 star F of G2 for all G1, G2 belonging to G. So here, this dot represents the binary operation in the domain group G, and this star represents the binary operation in the codomain G dash. A 1-1 and onto homomorphism is said to be an isomorphism. Therefore, a mapping is said to be an isomorphism if it satisfies 1-1 condition, onto condition, as well as the homomorphism condition. A homomorphism F from a group G into itself is called an endomorphism. Suppose if you consider a mapping F from G to itself, and if it is a homomorphism, then it is known as endomorphism. A 1-1 homomorphism is known as monomorphism. So a mapping is said to be a monomorphism if it satisfies 1-1 condition and the homomorphism condition. An onto homomorphism is called epimorphism. So a mapping is said to be an epimorphism if it satisfies onto condition and homomorphism. An isomorphism from a group G into itself, onto itself, is called an automorphism. So if you consider a mapping which is an isomorphism from the same group to same group, then it is said to be an automorphism. Next, let us move on to kernel of homomorphism. Let F from G to G dash be a homomorphism. So we are considering a homomorphism F from group G into G dash. And let G dash be the identity element of E dash be the identity element of G dash. The subgroup K of G, which is defined as K equal to set of all A belonging to G, such that F of A is equal to E dash. That is the set of all elements of G which are mapped onto the identity element of the codomain G dash, then such elements belong to kernel and it is denoted by the letter K. And this is known as kernel of homomorphism F, and it is denoted by ker F. Now let us move on to the fundamental homomorphism theorem. Let F be a homomorphism of a group G into a group G dash with kernel K. Then F of G is isomorphic image to the factor group G by K. So if you consider a homomorphism F from a group G into G dash with kernel K, then F of G, that is the image of F, that is F of G, which will be a subgroup of the codomain G dash, then that is said to be the isomorphic image of the factor group G by K. That is, G by K and F of G are isomorphic to each other. So let us prove this. Let us define the map psi from G by K to G dash. So we know that the elements of the factor group G by K will be of the form K into G, that is the coset generated by G with respect to K. And let us give the mapping psi of Kg is equal to phi of G for all G belonging to G and Kg belonging to G by K. So first let us prove that psi is well defined. So let us take two elements, Ka is equal to Kb, and now let us show that the image of Ka will be equal to the image of Kb. So Ka is equal to Kb implies that the element A belongs to the coset Kb. Since it belongs to the coset Kb, A can be written as K into B, where this small k belongs to the capital K. From here, we can operate with B inverse on either side, and we get AB inverse is equal to K, where K belongs to K. Now let us give the mapping under the function phi, because this K belongs to K implies that this is an element of the kernel. Therefore, the element is mapped onto the identity element E dash under the mapping phi. So phi of AB inverse will be equal to E dash. But phi is a homomorphism. Therefore, we can write this as phi of A into phi of B inverse, and that is equal to E dash. But phi of B inverse is nothing but phi of B whole inverse. This is from the properties of homomorphism. So we can write phi A into phi B whole inverse is equal to E dash. Now let us operate on either side by phi B. So we get phi of A, phi of B whole inverse into phi of B is equal to E dash into phi of B. Since E dash is the identity element of G dash, E dash into phi of B gives us phi of B. And on the left hand side, phi of B inverse into phi of B will give us the identity element E dash. So phi of A into E dash is equal to phi of B. But phi of A into E dash gives us phi of A. So phi of A will be equal to phi of B. But under the mapping psi, phi of G is equal to psi of Kg. Therefore, phi of A will be equal to psi of Ka, and phi of B will be equal to psi of Kb. So to begin with, we took Ka is equal to Kb, and now we proved that psi of Ka is equal to psi of Kb. Therefore, when the elements are equal, their images are equal. Therefore, psi is well defined. Now let us show that psi is 1, 1. So for that, let us assume the images of two elements are equal, and let us prove that the elements themselves are equal. So let us take psi of K is equal to psi of Kb, and that is equal to phi of K is equal to phi of B by the mapping definition of psi. Now operating on either side by phi of B whole inverse, we get phi of A into phi of B inverse is equal to E dash, because phi of B into phi of B inverse will give us E dash. Since phi is a homomorphism, now we can write this as phi of AB inverse, and that is equal to E dash. Since the image of this AB inverse is E dash, it belongs to the kernel K. Therefore, AB inverse belongs to K. Since AB inverse belongs to K, A belongs to KB. Since A belongs to KB, the coset generated by A will be equal to the coset generated by B, that is Ka is equal to KB. Therefore, psi is 1, 1. Since the images are equal implies the elements are equal. Therefore, psi is 1, 1. Now let us prove that psi is onto. So let us take an element in the codomain G dash. G dash belongs to G dash. Since G dash belongs to G dash, there exists a G belongs to G. Under the mapping phi, phi of G will be equal to G dash because phi is onto. Since we have found an element G belonging to G such that phi of G is equal to G dash, and under the mapping psi, phi of G is equal to psi of Kg. Therefore, G dash is equal to phi of G, and in turn that will be equal to psi of Kg, where Kg belongs to G by K. Therefore, psi is onto. Now let us prove that psi is a homomorphism. To prove that psi is a homomorphism, let us take psi of Ka into Kb. But Ka into Kb is the product of two right cosets, and that will be once again a right coset, that is Kab. So psi of Kab. Under the mapping psi, this is mapped down to phi of Ab. But phi is a homomorphism, therefore phi of Ab can be written as phi A into phi B. Now phi a can be written as psi of Ka and phi b can be written as psi of Kb. So to begin with, we took psi of Ka into Kb and we showed that that is equal to psi of Ka into psi of Kb. Therefore, psi is a homomorphism. Since psi is already 1, 1 and on 2, psi is a isomorphism. That is the mapping f from g by k to g dash is an isomorphism. Therefore, g by k is isomorphic to g dash. Now let us move on to the natural homomorphism, or it is also known as the canonical homomorphism. Let G be a group and H be its normal subgroup. Then G by H is homomorphic image of G with kernel H. That is the mapping f from G to G by H defined by f of x is equal to hx for all x belonging to G is a homomorphism, and it is known as the natural homomorphism, or sometimes it is also known as canonical homomorphism. Thank you.